Imagine a world where your smartwatch doesn't just track your steps, but truly understands your health data without ever sending it off to the cloud.
Yeah, or think about a factory robot that can predict its own failure, like in real time, stopping costly downtime before it even happens.
Or even your smart home camera, identifying an intruder, but crucially, keeping those images of your family securely on the device itself. This isn't science fiction anymore, is it?
Not at all. It's the rapidly unfolding reality of Edge AI.
And that's exactly what we're diving into today.
Mm-hmm. This deep dive is based on a really comprehensive guide to mastering Edge AI and also an excellent explanatory overview. So we've got both the conceptual stuff and the practical insights you'll need.
And our mission, as always, is to pull out the most important nuggets, giving you a shortcut, really, to understanding this, well, transformative field.
And transformative is the right word. I mean, consider this statistic. Projections indicate that a staggering 75% of enterprise-generated data is expected to be processed at the edge by 2025.
75%. Wow. That's up from what, just 10% back in 2021?
Exactly. So this isn't just some minor trend, it's a monumental shift. It's fundamentally reimagining our digital nervous system, you could say.
It's about empowering devices to act as these sort of autonomous mini brains, making decisions instantly, right where the data happens.
Precisely. It's a leap that unlocks possibilities that, yeah, were pure science fiction not long ago.
Okay, so let's unpack what Edge AI actually is at its core. What are we talking about?
Well, at its heart, it's about deploying and running AI algorithms, machine learning models directly on local hardware, right
Yeah.
where the data is generated.
So literally bringing the AI's brain down to the device itself.
Exactly.
How does that fundamentally differ then from the traditional cloud AI we're maybe more familiar with? Is it just about the location?
It's much more than just location, though that's part of it. With traditional cloud AI, you've got to send all that raw data up to remote servers, process it, get the answer back. There's a delay.
Right, the round trip.
The round trip. But with Edge AI, devices like industrial robots or your smart home assistant or autonomous drones, they can process information and make decisions independently.
So the smart speaker recognizing the wake word, hey Google or whatever, that happens locally.
Often, yes. Or a security camera identifying an intruder in real time. Or that factory machine predicting its failure. All potentially happening without needing a constant link back to some distant data center.
Okay, so what's really driving this shift? It feels like there must be some powerful forces pushing us towards the edge.
Oh, absolutely. It's not just tech for tech's sake. There are really strong business and technical reasons. The first, and arguably the most critical one, is ultra-low latency.
Latency. So delay. You mentioned the round trip. Can you give us an example where even a tiny delay, milliseconds, could genuinely mean the difference between, well, success and failure?
Definitely. Think about an autonomous vehicle detecting a pedestrian.
Right. Safety critical.
Absolutely. A fraction of a second delay could be fatal. Or in robotic surgery, you need those real-time insights from AI guiding the instruments. Precision is paramount.
Can't wait for the cloud on that one.
You really can't. And in smart manufacturing, detecting a tiny defect on a fast-moving assembly line and triggering an immediate action like ejecting the part, that just wouldn't be possible if you had to wait for a cloud response.
Okay, so these applications demand, like, near instantaneous responses,
Yeah.
milliseconds, edge is the only way.
For those use cases, pretty much, yeah.
Okay, so beyond speed, what about privacy and security? That's a huge concern these days. How does Edge AI help there?
That's another massive driver. Edge AI keeps sensitive data on the device itself. It embodies this principle we call privacy by design.
So my health data from my wearable, for example.
Exactly. It could be analyzed locally, on the watch, ensuring your sensitive medical info maybe never leaves your wrist. Or facial recognition data on your smart home camera, it stays local, preventing images from being uploaded unless absolutely necessary.
Which must simplify things like GDPR compliance, HEAPA.
Hugely. And it significantly reduces the attack surface, right? Less data traveling across networks means fewer opportunities for interception or breaches.
And what about just keeping things running? Reliability. Cloud systems need internet. What if that connection drops, especially in remote places?
Precisely. Imagine an oil rig out at sea or an agricultural drone flying over vast fields with patchy or no cell service. Edge AI systems are designed to operate autonomously.
They can just keep going.
Yes, even with intermittent or zero internet connection. A smart factory could continue basic operations during an internet outage, preventing really costly downtime. This robustness makes edge AI essential for many mission-critical applications where you just can't guarantee connectivity.
Okay, speed, privacy, reliability, big advantages. Is there a cost argument too? I mean, cloud storage is getting cheaper, but maybe the sheer volume of data is the issue?
That's a great point. Yes, it's very much about the volume. The sheer amount of raw data generated by potentially millions, billions of IoT devices, especially things like high-definition video, it creates a kind of data tsunami.
Right. Sending all of that to the cloud would be insane.
Exactly. Continuously streaming all that raw data is often economically unsustainable. You'd rack up massive bandwidth and storage bills. Edge AI acts as an intelligent filter.
Ah, okay.
It processes the raw data locally, figures out what's important, and then maybe only transmits the critical insights or alerts.
So instead of sending hours of video, it just sends person detected at 3:05 a.m.
Precisely. This dramatically cuts bandwidth usage and lessens the load on those expensive cloud servers. It makes large-scale IoT deployments economically feasible in a way that pure cloud often couldn't be.
Given all these benefits, it's really tempting to think, okay, edge AI is the future, goodbye cloud AI. But that's a misconception, right? They're not actually rivals.
You've hit on a really critical point there. They are absolutely not rivals. In fact, the most powerful AI systems we see today leverage a hybrid model. Edge and cloud work together, each playing to its strengths.
Okay, so what's the division of labor then?
Well, think of the cloud with
Yeah.
its virtually limitless computational power. It's perfect for the really heavy lifting, the resource-intensive task of training these large, complex AI models on massive data sets. That's where the model learns its fundamental intelligence, its knowledge base.
Right, training takes huge amounts of data and processing power. Makes sense to do that where resources are abundant.
Exactly. And then the edge, that's where this intelligence gets applied.
Right.
The trained, often optimized model is deployed down to those resource-constrained edge devices to perform what we call inference.
Inference being making predictions or decisions on new real-world data.
Precisely. So the cloud trains the brain, and the edge uses it in the real world.
Got it. But is it just a one-way street?
Yeah.
Trade in cloud, deploy to edge, end of story.
Not at all. And this is where it gets really interesting. It's actually a dynamic, continuous learning loop.
Okay.
So when an edge device encounters something weird, maybe data it can't confidently process, an unusual machine vibration it hasn't heard before, or an object it doesn't recognize, it can flag that.
And send that specific interesting data back up.
Exactly. It can upload that tricky sample back to the cloud. This real-world data then helps the data scientists retrain and fine-tune the central cloud AI model, make it smarter based on actual EDV experiences.
So the edge devices provide feedback from the front lines.
Precisely. Then the improved retrained model gets optimized again and redeployed back down to the whole fleet of edge devices. This enhances the intelligence of the entire system over time.
That dynamic feedback loop. That sounds like MLOps, machine learning operations, right? Managing that whole life cycle.
It's a cornerstone of modern MLOps, absolutely. That continuous improvement cycle is key.
Okay, this makes a lot of sense conceptually, but let's get tangible. Let's talk about the building blocks. Hardware first. When we say edge devices, what's the actual spectrum? Is it just phones and cameras?
Oh, it's incredibly vast. We can broadly categorize them into, say, 3 tiers. At the really low end, you have what we call constraint class devices. This is often where TinyML comes in.
TinyML, like really tiny.
Really tiny. Think microcontrollers like an Arduino Nano 33 BLE sense. These have extreme resource constraints. We're talking kilobytes of RAM, maybe running on a coin cell battery for months or years.
Wow, what can they even do with AI?
They're perfect for simple, always-on tasks, like keyword spotting, listening for Hey Siri without draining your phone battery, or simple anomaly detection in an industrial sensor, just looking for vibration patterns that are out of the ordinary.
Okay, so very specific low-power tasks. What's the next step up?
That's the performance class devices. And this, I'd say, is the main battleground for most edge AI developers right now.
This is where things like Raspberry Pi come in.
Exactly. Single board computers, like the Raspberry Pi, and also more specialized system on modules, or SOMs, like the NVIDIA Jetson series or Google Coral boards.
And these are more powerful.
Much more. They run full operating systems like Linux. They have gigabytes of RAM. And crucially, they often feature dedicated AI accelerators, little chips specifically designed to speed up AI calculations, like GPUs or TPUs.
So they can handle more complex stuff.
Absolutely. Real-time object detection in video streams, analyzing feeds from multiple cameras, more sophisticated predictive maintenance. This is where a lot of the exciting prototyping happens.
Okay, and the third tier,
That's the infrastructure class devices. These are the heavy hitters on the edge.
like servers, but local?
Kind of. Think industrial edge gateways or edge servers. They often sit on a local network, maybe in a factory or a retail store. They aggregate data from multiple smaller edge devices nearby.
So they collect data from sensors and cameras on the factory floor.
Right. And they have enough computational power to run several complex AI models simultaneously, doing more advanced analysis before sending maybe just the curated, aggregated insights up to the cloud. They act as a sort of local hub.
Got it. So for someone wanting to get started, maybe build a prototype, those performance class boards, the Jetsons, Corals, Pis seem key. Can we dive into those a bit? What are the pros and cons?
Definitely. Choosing the right board is critical because it really dictates your software path, your tools, your whole workflow. Let's look at the big three.
Okay, start with NVIDIA Jetson. I hear that name associated with power.
It absolutely is the powerhouse. The Jetson series, like the newer Orin Nano, is built around NVIDIA's very powerful GPU architecture. This makes it the go-to if you need serious computational muscle for demanding AI tasks.
Like analyzing multiple high-res video streams at once.
Exactly. Complex video analytics, high-resolution image processing. Its biggest strength, arguably, is the incredibly rich and mature software ecosystem. The Jetpack SDK, CUDA, TensorRT. This gives you maximum flexibility. You can pretty much run optimized models from any major framework, TensorFlow, PyTorch, on an X.
And performance. You mentioned TOPS earlier.
All right, tera operations per second.
Yeah.
The Jetson Orin Nano can deliver up to 40 TOPS for INT8 calculations. That's integer math, which is very efficient for AI inference. It's a lot of performance for an edge device.
What's the catch? Price? Power?
Both, to some extent. Jetsons tend to consume more power, maybe in the 5 to 15 watt range, depending on the model and workload. And they have a higher price point, perhaps around $249 for something like an Orin Nano developer kit. So more power, more flexibility, but higher cost and energy use.
Okay, so Jetson for the heavy lifting. What about Google Coral? That seems positioned differently, more around efficiency.
That's exactly right. Google Coral, whether it's the dev board or the little USB accelerator stick, is the efficiency expert. Its defining feature is the Edge TPU.
TPU. Tensor Processing Unit, Google's custom AI chip.
Precisely. It's an ASIC, an application-specific integrated circuit designed from the ground up to do one thing really well: execute quantized TensorFlow-Lite models very, very quickly and with incredibly low power consumption.
How efficient are we talking?
It delivers about 4 TOPS, but typically while consuming only around 2 to 4 watts. That's a fantastic performance per watt ratio.
Wow, so perfect for battery-powered things.
Exactly. Or thermally constrained devices where you can't have a big fan. Think smart cameras, mobile robots, portable sensors, anywhere power matters most.
But there must be a trade-off.
The main trade-off is flexibility. The Edge TPU is really optimized for and almost exclusively supports TensorFlow-Lite models that have been specifically compiled for it. So you're pretty much locked into that T-Flight ecosystem.
Okay, less versatile than Jetson, but super efficient for T-Flight. What about cost?
Generally lower than Jetson. You might get a Coral Dev Board Mini for around $100 or the USB accelerator for about $60, so more accessible financially.
And then there's the Raspberry Pi, the hobbyist favorite, the versatile workhorse. How does it fit into the serious edge AI picture? Can it really compete?
The Pi, especially the 4, the newer 5, is the most accessible and affordable entry point, absolutely. And it has that massive community support, which is huge. Now, on its own, its CPU isn't really powerful enough for demanding AI inference tasks.
Right, running complex models directly on the Pi's brain is slow.
It can be, yeah. But its real potential for edge AI is unlocked when you pair it with an external AI accelerator.
Ah, so you add on a specialized chip.
Exactly. The most common and popular combination is probably a Raspberry Pi 5 plus a Google Coral USB accelerator. You plug that $60 stick into the Pi's USB 3 port, and suddenly you have those 4 TOPS of efficient T-Flight acceleration.
So you get the Pi's flexibility and low cost, plus the Coral's AI boost.
Precisely. It's a great modular approach. Another powerful option now, especially with the Pi 5's faster PCIe interface, is using an accelerator HAT, like the Halo 8.
It's like a little board that sits on top.
Yeah. Something like the Halo 8 M.2 AI module, connected via a suitable adapter, can deliver a really impressive 13 to 26 TOPS. That's getting into serious performance territory.
So the Pi becomes a platform you build upon. Strengths or cost, community, flexibility via add-ons. Downsides.
Well, performance can sometimes be influenced by the interface you're using, USB versus PCIe. And you're integrating components, potentially drivers and software, from different ecosystems, which can sometimes add a bit of complexity compared to an all-in-one solution like Jetson. Power consumption also goes up when you add accelerators, though the base Pi is very low power, maybe 2.6 watts.
Okay, that gives a great overview of the hardware choices. Now the software. You need something to actually run the models on these devices. You mentioned runtimes.
Yes. Think of a runtime as a specialized engine. It takes your trained AI model file and executes it efficiently on the specific hardware you have, taking advantage of any accelerators present.
And TensorFlow Lite, TF Lite, is a big one, especially with Coral.
It's huge. TensorFlow Lite is Google's official framework for on-device ML. It's widely used, especially for Android devices, and yes, anything using Google's Coral Edge TPU. It converts standard TensorFlow models into a compact .tflight format.
And its focus is
Low latency, small binary size, so the runtime itself doesn't take up much space, and leveraging hardware acceleration through things called delegates.
delegates. What are they?
A delegate is basically a piece of software that tells TFlight, hey, instead of running this part of the model on the main CPU, offload it to that specialized hardware like the GPU or a DSP, digital signal processor, or the edge TPU. It unlocks the hardware's potential.
Makes sense. What about ONNX runtime? You mentioned it earlier, the universal translator.
Right. ONNX, the Open Neural Network Exchange format, and its associated ONNX runtime are incredibly important for interoperability. AI development is fragmented, right? People train models in TensorFlow, PyTorch, scikit-learn, many different frameworks.
Yeah, it can be a mess trying to deploy models trained in different places.
Exactly. ONNX provides a standard format. You can train your model in, say, PyTorch, export it to the .onx format, and then use the highly optimized ONNX runtime to execute that same file efficiently on a huge variety of platforms. Cloud servers, Windows PCs, Linux edge devices, mobile phones.
How does it optimize the execution?
It performs extensive graph optimizations.
Mm-hmm.
It analyzes the structure of your model and does things like fusing multiple simple operations into a single, more complex but much faster operation tailored for the hardware.
Yeah.
Its cross-platform, cross-framework nature makes it super valuable.
Okay, so T-Flight for Google Android Coral ecosystem, ONNX runtime for broad interoperability. What if you're primarily a PyTorch developer? Is there a direct path?
Yes, absolutely. For PyTorch folks, there's PyTorch Edge. Historically, the main path was converting PyTorch models to something called TorchScript, which creates a static, serializable version of the model.
That's evolving.
It is. More recently, Meta introduced ExecuTorch. This is designed to be an even more lightweight, portable, and flexible runtime specifically aimed at resource-constrained edge devices, even down to microcontrollers. It aims for a more direct and efficient deployment path right from PyTorch training. It's definitely a key framework to watch as it matures.
Got it. So we have the hardware, we have the software runtimes, but now comes what sounds like the real challenge, the real art for an edge AI engineer. Taking those massive, powerful models trained in the giants and shrinking them down, making them fit and run efficiently on these tiny edge devices.
You're absolutely right. This is where a huge amount of the effort, innovation, and frankly, the difficulty lies in edge AI development.
What's the fundamental trade-off you're always battling?
It boils down to accuracy versus performance. And performance here is multifaceted. It's inference speed, latency, it's memory footprint, how much RAM it needs, and it's power consumption. Generally, more complex models are more accurate, but they're also bigger, slower, and hungrier for power.
So the engineer is constantly juggling. Okay, if I make the model simpler to run faster, how much accuracy do I lose? Is that acceptable for this specific product?
Exactly. It's not just a technical puzzle, it's often a product and business decision. Is a 2% drop in accuracy acceptable if it means we get a 50% reduction in latency, or maybe doubles the battery life of the device? Those are the tough calls.
How do they make those calls? What tools do they use to shrink these giants? What's in the optimization toolkit?
There's a set of really powerful techniques, and crucially, they're often combined for the best results. The first one, and often the most impactful, is quantization.
Quantization. We touched on that with T-Flight and the Edge TPU. It's about reducing numerical precision.
Right, exactly. Most AI models are trained using 32-bit floating point numbers, FP32, which offer high precision. Quantization reduces that precision, often down to 8-bit integers, INT8, or sometimes 16-bit floats, FP16.
And the benefits of using smaller numbers.
They're substantial. First, model size. Moving from FP32 to INT8 roughly shrinks your model file size by 4 times. That's huge for devices with limited storage. Second, memory usage drops. Third, Inference speed. Integer math is generally much faster for processors than floating point math. And fourth, energy savings. Integer operations consume significantly less power, often reductions of 75% or more are cited.
4 times smaller, faster, less power.
Yeah.
Sounds amazing. Are there different ways to quantize? You mentioned post-training versus quantization aware.
Yes, two main flavors. Post-training quantization, PTQ, is the simpler approach. You take your already trained FP32 model and convert it to INT8 afterwards. It's quick, doesn't require access to the original training data or pipeline. The downside, it can sometimes lead to a noticeable drop in accuracy because the model wasn't originally aware it would be running at lower precision.
So quick and easy, but might hurt accuracy. What's the alternative?
Quantization-aware training, QAT. This is more advanced. You actually simulate the effects of quantization during the training process itself. The model learns to adapt to the lower precision while it's being trained.
Ah, so it compensates for the precision loss during training.
Exactly. The result is usually a quantized model with much higher accuracy, closer to the original FP32 model compared to PTQ. But the downside is that it's more complex, takes longer, and requires you to have access to the training data and the training pipeline.
So PTQ for maybe less critical applications or faster prototyping, QAT when accuracy is absolutely paramount.
That's a good rule of thumb, yes.
Okay, quantization is one tool.
Yeah.
What else? You mentioned trimming the fat earlier, pruning.
Right, pruning. Neural networks often have a lot of redundancy. Many connections or weights might be very close to zero or simply not contributing much to the final output. Pruning techniques identify and remove these unimportant weights or connections, effectively setting them to zero.
Creating a sparse model, like full of holes.
Exactly. This makes the model file smaller. And importantly, if you have hardware or software runtimes that are sparsity aware, meaning they know how to efficiently skip over those zeroed out calculations, it can also speed up inference.
Do you lose accuracy when you prune?
You often do initially, but a common practice is to do some fine-tuning, a bit more training after pruning to help the remaining weights adapt and recover most of the lost accuracy.
Okay, trimming the fat. What about knowledge distillation? You described it as a student learning from a master. Sounds elegant.
It really is quite elegant. The idea is you first train a large, complex, highly accurate teacher model, probably in the cloud. Then you train a much smaller, simpler student model, which will be your edge model.
How does the student learn from the teacher?
Instead of just learning from the basic data labels, like cat or dog, the student also learns to mimic the output probabilities of the teacher model. The teacher might say, I'm 95% sure this is a cat, but maybe 4% dog and 1% rabbit. Those nuanced soft labels contain more information than just the hard label cat.
Ah, so the student learns the teacher's reasoning, not just the final answer.
Exactly. By learning from the teacher's richer output, the smaller student model can often achieve significantly higher accuracy than if it were just trained on the hard labels from scratch, despite its much smaller size. It effectively transfers the knowledge from the big model to the small one.
Clever. Quantization, pruning, distillation. Anything else in the main toolkit?
The final, absolutely crucial step is hardware-specific compilation.
This is where tools like NVIDIA's TensorRT or the Google Edge TPU compiler come in?
Precisely. You take your optimized model, maybe it's been quantized and pruned, and you feed it into a compiler specifically designed for your target hardware. Jetson GPU, Coral Edge TPU, maybe an Intel VPU via OpenVINO.
And what does this compiler do?
It performs aggressive, low-level optimizations that are tailored exactly for that chip's architecture. Things like layer fusion, combining multiple sequential layers, like convolution, batch norm activation, into a single, highly optimized kernel that runs much faster. Precision calibration, intelligently deciding which layers benefit most from INT8 versus maybe keeping some in FP16 or even FP32 for accuracy. Tensor memory layout optimization, rearranging how data is stored in memory to maximize access speed for that specific hardware.
So it's taking the generic optimized model and transforming it into a super efficient executable engine custom built for that one chip.
That's a perfect way to put it. This step is often where you see the biggest final leap in performance and efficiency. It's absolutely critical for getting the most out of your edge hardware.
Wow, okay, that's a lot of complex optimization. It really helps to see how this all comes together. Can we walk through a practical example, maybe building that smart security camera we talked about earlier?
Absolutely. A smart security camera is a great example because it touches on all these key concepts: local processing for privacy, low latency for real-time detection, offline reliability, minimizing bandwidth.
And the hardware setup we discussed. Raspberry Pi 5 plus a Google Coral USB accelerator.
Yeah, that's a very popular and powerful combination for prototyping something like this. The Pi runs the main application logic, handles the camera feed, networking, etc., and the Coral accelerator handles the heavy lifting of the AI inference, specifically the object detection, very efficiently.
Okay, so if we were building this,
Yeah.
what's the workflow? What are the steps? Sounds like step one is setting up the hardware and software environment.
Right. Get your Pi 5, connect the camera module, plug in the Coral USB stick, install Raspberry Pi OS. Then you need the core software, the TensorFlow Lite runtime, the T-Flight runtime Python package. You'll need OpenCV, OpenCV-Python for handling the video frames. And importantly, you need the specific Coral Edge TPU runtime library from Google, which allows T-Flight to use the accelerator.
So getting all the basic plumbing working. Then step two, data collection and labeling. Crucial if we want to detect something specific, like packages on the porch.
Absolutely critical for any custom object detection. If you just want to detect generic people or cars, you might use a pre-trained model. But for specific things like your brand of delivery boxes or maybe distinguishing squirrels from cats, you need custom data.
How much data?
For a simple project, maybe start with 100 to 200 images of your target objects. Capture them in different lighting conditions, different angles, different backgrounds. Variety is key. Then use a labeling tool.
Like?
Tools like MakeSense.ai, LabelMG, or cloud platforms like RoboFlow. You basically draw bounding boxes around the objects in each image and assign them a label, package, person. This creates your data set. High-quality labels are vital here, garbage in, garbage out.
Okay, data collected and labeled. Step three, model training. And this happens in the cloud, right? Not on the Pi.
Correct. Training object detection models is computationally expensive. You typically use a cloud platform with GPU access like Google Colab, AWS SageMaker, or Azure ML.
And what kind of model would you train?
You'd choose an architecture that's already designed for efficiency on edge devices. Popular choices are families like MobileNet V2 SSD or Efficient Detlight. You wouldn't start from scratch. You'd use transfer learning.
Meaning you take a model already trained on a huge data set, like ImageNet, and just fine-tune it on your relatively small custom data set.
Exactly. Tools like the TensorFlow Lite Model Maker library simplify this process dramatically. It handles loading your custom data, performing the fine-tuning, and helps with the next steps too.
Which brings us to step four, model conversion and compilation. This is where the shrinking happens.
Yes, this is the critical optimization stage for our Pi plus Coral setup. Using tools like Model Maker or the T-Flight Converter API, you'd first perform post-training quantization. Specifically, you'd want full integer quantization, INT8, because that's what the Edge TPU is designed to accelerate most efficiently.
So convert the fine-tuned model to INT8. That shrinks it by about 4x. What next?
Then you take that quantized.tflight model and compile it specifically for the Edge TPU using Google's EdgeItCompiler command line tool. This analyzes the model and optimizes it further for the Coral chip, producing a new file, usually ending in edgeitprut.tflight. That's the file you'll actually run on the device.
Right, the hardware-specific compilation step. And you mentioned iteration here earlier.
Yes, this stage often involves some trial and error. Maybe the first quantized model isn't accurate enough, so you might need to tweak quantization parameters or even consider QAT, or perhaps you try different model architectures. It's rarely a single linear pass in a real project.
Okay, model trained, quantized, compiled. Step five, on-device application development. Writing the actual Python code for the Pi.
Exactly. You transfer your compiled edgeitprut.tflight model file and a label map file, which tells the code what class 0 means, e.g. person, over to the Raspberry Pi. Then you write the Python script.
What does the script do?
It typically uses OpenCV-Python to capture frames from the camera. For each frame, it pre-processes the image, resizing, normalizing pixel values to match what the model expects. Then, it uses the T-Flight runtime library, specifically pointing it to the Edge TPU delegate and your compiled model, to run the inference. The inference gives back bounding boxes, class labels, and confidence scores. Finally, the script might draw those boxes on the frame using OpenCV and display it, or trigger an alert if a person is detected with high confidence.
So a loop, grab frame, prep, infer, show act.
Pretty much, yeah. That's the core inference loop.
Step six, benchmarking and validation, making sure it actually works well in practice.
Absolutely. You need to measure its real-world performance. How fast is it? You typically measure frames per second, FPS. How many video frames can it process each second? You also want to measure the pure inference latency. How many milliseconds does just the AI part take?
And you compare maybe running on the Pi CPU versus the Coral accelerator.
Exactly. That demonstrates the value of the accelerator. For more advanced analysis, you could even hook up a USB power meter and measure the actual wattage consumed during inference, proving the power efficiency gains as well. And of course, qualitatively, you just watch it run. Is it detecting the objects accurately? Are there false positives?
Right. Does it actually work?
Yeah.
And the final step, step 7, introduction to edge MLOps. This sounds like scaling up from a prototype?
It is. This is what separates a cool demo from a deployable, maintainable product, especially if you have more than one device. Edge MLOps deals with the infrastructure around the model.
Like this.
Things like automated deployment pipelines using tools like Jenkins or GitHub Actions to automatically retrain, convert, compile, test, and deploy new model versions. Secure over-the-air OTA updates. How do you safely push that new model file out to hundreds or thousands of devices already installed in homes or factories? And performance monitoring. How do you track if the model's accuracy is degrading over time in the real world, model drift, and maybe trigger a retraining cycle?
Okay, so that's the whole life cycle management. Crucial for production.
Absolutely essential for anything beyond a hobby project.
This is fascinating. Looking ahead now, the field's moving so fast. What are some of the advanced topics and future trends we should be keeping an eye on? You hinted that the cloud train's edge infers division might be blurring.
It absolutely is. One of the most exciting trends challenging that paradigm is training on the edge, specifically through techniques like federated learning.
Federated learning, I've heard that term. It's about training models collaboratively across devices without sharing the raw data, right?
Exactly. It's a revolutionary technique for privacy-sensitive applications. Imagine multiple edge devices, maybe phones, maybe sensors in different hospitals, collaboratively training a single shared AI model without ever sending their raw private data to a central server.
How does that work then, if the data stays put?
Well, typically, a central server sends out the current version of the global model to participating devices. Each device then trains that model locally, using only its own data. Then, instead of sending the data back, it sends back only the updates it made to the model parameters, often encrypted or anonymized updates.
And the central server aggregates these updates from many devices.
Right. It aggregates these updates to create an improved global model, which is then sent back out for the next round of local training.
Wow. So the collective intelligence improves, but the private data never leaves the local device.
Precisely. Think about hospitals collaborating to train a better diagnostic model without ever sharing confidential patient records, or a fleet of autonomous vehicles learning from each other's driving experiences without uploading sensitive location or video data. It's a potential game changer for privacy. Frameworks like TensorFlow Federated, TFF, and Flower are making this increasingly practical.
That's huge. What else? You mentioned TinyML earlier, AI on a diet. Taking edge AI to the absolute extreme.
Yes, TinyML is all about deploying ML models onto those tiny microcontrollers, MCUs. We talked about devices running on milliwatts of power with maybe only kilobytes of memory.
Running for years on a battery.
Potentially, yes. This enables a whole new class of always-on intelligent sensing. We already see it in keyword spotting. Hey, Siri. But think about tiny, cheap, predictive maintenance sensors you could stick on every motor in a factory. Or on-device analysis for fall detection in medical wearables. Or smart agriculture sensors analyzing soil conditions right in the field. It's bringing simple intelligence to the smallest, most power-constrained places.
Amazing. And the really big buzzword now, generative AI. Is that coming to the edge too? Seems incredibly difficult given the size of models like GPT or Stable Diffusion.
It is incredibly difficult, but yes, that's definitely the next major wave, generative AI on the edge. Moving beyond analytical models, classification detection, to running large language models, LLMs, and image audio generation models locally on edge devices, maybe even phones or laptops.
What would be the benefit of running, say, an LLM locally?
Imagine hyper-personalized, context-aware, and completely private user experiences that don't rely on sending your queries or data to the cloud. Your smart refrigerator could suggest recipes based only on its local knowledge of the contents and your stated preferences without pinging a server. Factory robots could perhaps be given new instructions using natural language, interpreted locally. Industrial machines might generate human-readable summaries of complex error logs right on the spot.
Giving devices the ability to reason, create, and communicate locally.
Exactly. The challenges are immense. These models are huge, computationally very expensive. But we're seeing rapid progress. Google's Gemini Nano, designed for mobile devices, is an early example. Qualcomm, Apple, Intel, everyone is working on hardware and software to make this feasible. It's a huge area of research and development.
With all this intelligence being pushed out to potentially billions of devices, security and privacy become even more critical and maybe more complex.
Absolutely paramount. And yes, the distributed nature introduces unique vulnerabilities. A device out in the physical world is potentially accessible to attackers in ways a cloud server isn't. A security-first mindset is just non-negotiable.
What kind of threats are specific to edge AI?
We need serious threat modeling and understanding potential adversarial attacks. Frameworks like MITRE Atlas help map out edge-specific threats. Key risks include data poisoning, where an attacker might subtly corrupt the data used for local training or federated learning to degrade the model. Model stealing or inversion, where an attacker interacts with the device repeatedly to try and reconstruct the AI model itself, or worse, infer sensitive information about the original training data.
And those adversarial attacks we hear about, like stickers on stop signs fooling self-driving cars.
Exactly. Adversarial examples are a huge concern. These are tiny, often human imperceptible changes made to the input data and image, audio, that can cause the AI model to make a catastrophic error misclassifying an object, ignoring a command. Defending against these requires robust testing and techniques like adversarial training, where you deliberately train the model on such tricky examples.
So beyond just keeping data local, which edge AI helps with, there are more advanced privacy-preserving machine learning techniques needed too.
Yes. Techniques are emerging like homomorphic encryption, which sounds like science fiction but allows you to perform mathematical computations directly on encrypted data without ever decrypting it. And differential privacy, which involves adding carefully calibrated statistical noise to data or model updates, making it mathematically very difficult, ideally impossible, to identify any individual's contribution to the overall result.
Wow, and complex stuff. What about more standard security best practices?
They're still fundamental. You need a multi-layered zero-trust approach. Data encryption, both when stored on the device at rest and when transmitted in transit. Hardware-level security, using things like secure boot processes and trusted execution environments, TEs, to protect keys and model execution. Strong authentication and access control to prevent unauthorized use or modification. And as mentioned with MLOps, secure over-the-air OTA updates are crucial for patching vulnerabilities in both the device firmware and the AI models themselves.
It really sounds like a field that requires a unique blend of skills.
Yeah.
What's the profile of a successful edge AI engineer? What do they need to know?
It's often described as being a T-shaped professional. You need deep expertise in a few core areas, but also broad knowledge across the entire stack.
Like, what's the deep part of the T?
The core competencies are definitely ML model optimization, deep understanding, and hands-on skill with quantization, pruning, knowledge distillation. Embedded systems programming proficiency, typically in Python, but often also C++ for performance-critical parts or microcontroller work. And mastery of ML frameworks for the edge, like TensorFlow Lite, OnNX Runtime, PyTorch Edge Executorch.
And the broad top of the T.
That's broad knowledge across. Hardware platforms familiarity with the trade-offs of Jetson, Coral, Pi, MCUs, etc. Understanding data pipelines and MLOps, the whole end-to-end model lifecycle, including deployment and OTA updates. And really important, cross-functional collaboration skills, being able to talk effectively with hardware engineers, software developers, data scientists, and product managers.
So it's not just about building a model, but getting it deployed and working reliably in the messy real world.
Exactly. Employers are looking for engineers who can bridge that gap, who can deploy and maintain models in resource-constrained, real-world environments and show measurable improvements in performance, efficiency, or cost.
For listeners inspired by this, maybe wanting to become that T-shaped professional, what's a sensible learning roadmap? Where should they start?
It can seem daunting, but a structured approach helps. First, get the foundations right. Solid understanding of linear algebra, calculus, probability, statistics, and strong Python programming skills. That's the bedrock.
Then specialize.
Then dive into specialized courses or content. Look for things focusing on the intersection of AI and IoT or embedded systems. There used to be things like the Intel Edge AI Nano degree. Now you might find similar modules on Coursera, EDX, or provider-specific training from NVIDIA or Google. Essential books like AI at the Edge or TinyML are great. And crucially, explore open-source projects and repositories. NVIDIA's Jetson inference examples, Google's Coral examples on GitHub, platforms like Edge Impulse for TinyML.
And the most important thing,
Hands-on experience. Nothing beats actually getting aboard a Pi with the Coral Stick is a great start to finding a small project, like our smart camera, but maybe simpler, and just start building, tinkering, debugging. That practical experience is absolutely irreplaceable.
Fantastic. Well, there you have it, our deep dive into the fascinating world of Edge AI. We've journeyed from its core concepts and powerful drivers, latency, privacy, reliability, cost, through the hardware, the software, the critical optimization techniques.
To a practical project example, and finally looked at the exciting future trends like federated learning, TinyML, on-device generative AI, and the crucial aspects of security and the skills needed.
We really hope this has given you a clear roadmap to understanding this incredibly dynamic and rapidly transforming field, highlighting that unique blend of machine learning and embedded systems engineering.
And as we wrap up, maybe leave you with a thought. In a world that's becoming increasingly saturated with connected devices, Edge AI isn't just about making technology faster or cheaper or more private, though it does all those things.
It's really about something more fundamental, isn't it?
It is. It's about empowering these devices to truly perceive, interpret, and react to our physical world with a level of intelligence and autonomy that was previously impossible.
So, the final question for you to ponder. What kind of truly intelligent systems will we build, will you build, when every device can truly think for itself?